Hello, this is Jude Socrates, and welcome to A Portrait of Linear Algebra. Our video for today is about the two key properties of the determinant function. So what are these two properties? So today we will learn and we will prove that the determinant is a litmus test for invertibility. So this says that a matrix is invertible if and only if its determinant is not zero. The second property is that the determinant function is multiplicative. So this means that if A and B are n by n matrices, then the determinant of the product A times B is the product of the determinant of A and the determinant of B. So we are used to linear transformations being additive, but in this case, the determinant function is multiplicative. It is not true in general that the determinant of A plus B and the determinant of A plus the determinant of B are the same number. So, to prepare ourselves to prove these two theorems, we are going to review several key theorems that we have seen in the past several sections. So our first two theorems are about the REF of a square matrix. So back in chapter 1, theorem 1.5.3, we saw that there are exactly two possibilities for the REF of an n by n matrix. We will either get the identity matrix, In, or the REF will contain at least one free variable and at least one row of zeros. And it turns out that if you have R leading ones, and remember that R means the rank of your matrix, then the number of free variables in the REF is n minus R, and this is also the number of rows of zeros in R. Fortunately, we're not really going to need this somewhat icing on the cake. We just need that the second possibility is that we will have a row of zeros. The second theorem relating to the REF is about invertibility. So in chapter 3, theorem 3.7.5, we saw that an n by n matrix A is invertible if and only if the REF of that matrix is the identity. So conversely, this says that if you see a row of zeros in your REF for A, remember in the algorithm, you put A on the left and the identity on the right. So if in the case of row reductions, you produce a row of zeros, you can stop because the matrix is definitely not invertible. So while we're talking about rows of zeros, we proved in the last section that if you have an n by n matrix with a row of zeros, then the determinant of that matrix must be zero. In that section, we also saw special formulas for the determinant of a triangular matrix, whether it is upper or lower triangular. So in particular, this also works for diagonal matrices. So we said that in all of these cases, the determinant of the matrix is simply the product of the diagonal entries. So you take A11 times A22 all the way down to ANN. And of course, fair warning, this only works if your matrix is upper or lower triangular. It obviously does not work in general. So now let's bring back three theorems which concern elementary matrices. An n by n matrix A is invertible if and only if it can be expressed as a product of elementary matrices. And we saw that in that algorithm where you put A on the left and the identity on the right, the sequence of row operations that we use in order to bring A to its REF of IN can be used to factor A into elementary matrices. So basically what we do is we reverse each step that we do and express it in terms of the corresponding elementary matrices. And then the product in that order should give us back the original matrix A. So for our next theorem that we are reviewing, if you have an elementary matrix E and you obtain E from the identity by multiplying one row of E of the identity by K, then the determinant of that elementary matrix is just K. If you obtain E by swapping two rows of the identity, then the determinant of that elementary matrix is -1. But if you just add a multiple of one row to another row of the identity, then the determinant of that matrix is +1. And type 3 is probably the easiest to prove because when you do that, you get an upper or a lower triangular matrix. All right, so this tells us that the determinant of every elementary matrix is a non-zero number. In a type 1 operation, K is not allowed to be 0. -1 and +1 are obviously not 0. So the final theorem that I want to review with you has to do also with performing an elementary row operation on a random matrix A. So suppose that A is an n by n matrix and B is obtained from A by a type 1 operation multiplying row I of A by a non-zero number K. Then the determinant of this new matrix B is K times the determinant of the original matrix A. Similarly, if we exchange row I and row J of A to produce B, then the determinant of B is the negative of the determinant of the original matrix A. And finally, if we add K times row I of A to row J of A, a type 3 operation, we don't change the determinant. The determinant of the new matrix B is exactly the same as the determinant of the original matrix A. And of course, we can also do column operations. So this tells us, remember that performing an elementary operation on a matrix can be done by encoding that operation using an elementary matrix. So you perform exactly the same operation that you want to do on the identity instead of A, thus producing an elementary matrix E. So if E is this matrix corresponding to that row operation, then to produce B, you multiply A to the left by E. And what this theorem tells us, remember, is that, well, K is the determinant of type 1 operation, -1 is the determinant of type 2, and +1 is the determinant of type 3. So this told us that the determinant of B is the same as the determinant of the elementary matrix B times the determinant of the original matrix A. And of course, E times A gives us this new matrix B. As a bonus, we get that if you multiply A by K, the determinant of that scalar product is K to the n times the determinant of that matrix A. We're not going to need that in this section. Okay, so now it's time to get down to business, and we are going to prove the first property of the determinant function, and that is a matrix A is invertible if and only if its determinant is not 0. So we're going to put everything we've learned together. So remember that we can get the REF of a matrix, let's call that R, by applying a sequence of elementary row operations. And remember, the last theorem that we saw said that if you want to perform an elementary row operation on a matrix, it's the same as multiplying it to the left by the corresponding elementary matrix. So, starting with A, we perform a row operation, then another, then another. Let's say we perform a total of P elementary row operations until we get the REF of our matrix. Okay, so now we will apply the formula from the last theorem, which was if B is E times A, where E is elementary, then the determinant of B is the determinant of E times the determinant of A. So the key here is that all of these matrices are elementary. So if you want the determinant of R, start on the left. This theorem, this formula tells us that we can factor out the determinant of ET and then multiply that by the determinant of the rest of this product. But we can keep going. Now we have ET minus 1, another elementary matrix, so we can take that out of the product. So let's make another line. So we can take out ET minus 1 from the determinant. I will make another copy of that, and I will change the subscript to ET minus 1. And we have the rest of the product. So that will now be ET minus 2. Okay? And obviously we can keep going. All right? So we go dot, dot, dot. And at the end of the day, we will have every elementary matrix from ET down to E1. And we still have, at the very end, the determinant of A. Okay, so quick review. We have R starting with this long product, ET down to E1, and then A. So the determinant of R is the determinant of ET times the determinant of ET minus 1. Factor them all out, all the way down to the determinant of E2 times the determinant of E1 times the determinant of A. Okay, so what are we going to do with this formula? We are going to split our analysis into two possible cases. So this was the first theorem that we reviewed, I do believe. We said that there are two possible REFs for a square matrix. It can either be the identity matrix or it will have a row of zeros. But what else did we see? If the REF is the identity, then we can say that A is invertible, right? But if it has a row of zeros, then we can say that A is not invertible. Okay. So what else will happen? Well, R is the identity. What is the determinant of the identity? I believe that we will get 1. So furthermore, we get on the left side 1, and then we get this long product. However, we said that for an elementary matrix, the determinant is either K, or -1, or +1, none of which are 0. Okay, so this long product is not 0. Okay, so if the left side is 1, and this portion of the right side is not 0, then the determinant of A cannot be 0 either. And so the determinant of A is not 0 either. Okay, so think about it. If that were 0, then we'll get 1. 0 times anything is 0. Ooh, we're back to chapter 0. Second case. If your REF has a row of zeros, A is not invertible. And what about R? Well, R has a row of zeros, so the left side is now 0. Furthermore, we get the left side is now 0, and the right side is the same. So we have these. Okay, but now, once again, none of these factors is 0. So we can divide the right side, both sides of this equation, by all of these factors. We get 0 divided by all of these equals the determinant of A, and thus the determinant of A has to be 0. Okay, so there you go. We reached a fork in the road on one branch of that proof. We saw that if the REF is the identity, then A is invertible, and the determinant of A is not 0. The other branch, R has a row of zeros. Then we get that A is not invertible, and furthermore, the determinant of A has to be 0. Okay, so we saw that the determinant formula is kind of really complicated. Okay, you have all of these products and you have to find the sign of the permutation and all that. And we can either get 0 or we can get a different number. Well, there's only one 0 and there are lots of non-zero numbers. So this tells us that if you randomly create a square matrix, how about a 4 by 4? Let's make it big. If you just randomly put in numbers into this matrix, you would have to be really, really unlucky, I guess, or lucky, to get a determinant of 0. Okay, let's check. Let's put 7, 3, -2, 4, 0. Okay, let's put a 0 in. 1, -9, 3, how about 4, how about 5, how about the -5? What haven't we put in there? Oh, I don't see an 8. Well, we can put in a 2-digit number, 17, -7. Okay, how about that? A completely random 4 by 4 matrix. What would you bet that this determinant is 0? Yeah, I don't think that's a winning bet. Compute matrices determinant. Yeah, far from 0. So the theorem that we just did said, well, that determinant is not 0, therefore the matrix is invertible. So compute matrices. Do you have an inverse? Yeah, and check it out. 2, 2, 7, 4 does appear in one of the entries of this matrix. Okay, so obviously if you multiply, now what about these other denominators? Okay, are they divisible, or are they factors rather of 2, 2, 7, 4? Let's find out. If you multiply that whole thing by 2, 2, 7, 4, you get all integers. So yes, there actually is a formula for the inverse of a matrix that uses the determinant. Okay, it's not a very practical way to get the inverse. Okay, you're still better off using Gauss-Jordan or row operations in general. Okay, so if it were completely random, then yeah, you will not get a matrix which has determinant of 0. Okay, so you have to work. You have to work hard to get a matrix that does have determinant 0. It can't be just completely random. What's an easy way to do it? Well, we said that a matrix is invertible in that really big theorem. One of the conditions is that the rows are linearly independent. Okay, so if the rows were dependent, then the matrix will not be inverted. So let's take the first 3 rows. Okay, all we have to do is make a linear combination. Okay, so why don't we double the first row and then subtract triple of the second row, and how about add 7 of the third row? Okay, that's the linear combination. We are going to get, that matrix. Okay, not so random matrix. So what do we have to do? We will replace the 4th row with that linear combination. Okay, so now we can ask, compute matrices determinant. Now its determinant is 0, because according to our last theorem, a matrix is invertible if and only if its determinant is not 0. This matrix is not invertible because we force the fourth row to be a linear combination of the first three rows. So therefore, the rows are not linearly independent. Okay, so can we find an inverse for this? Let's see if we can trick Maple. Compute matrices inverse. No, you cannot trick Maple. This matrix does not have an inverse. Okay, so now that we have proven the first property, we're going to use it to prove the second property, which is the multiplicative property. Suppose that A and B are n by n matrices. Then the determinant of the product A times B is the product of the determinant of A with the determinant of B. So in this proof, we will again use a case-by-case analysis, but slightly different. In the first case, A is invertible. So obviously in the second case, A will not be invertible. So in that case, we can write A as a product of elementary matrices. So again, let's write A as ET times ET minus 1 all the way down to E1. So I guess I should have an ET minus 1. There you go. So, just like last time, we get the determinant of A is the determinant of this long product. We can factor out the ET and then the ET minus 1. Keep going until you factor it all the way down to E1. Okay, so in the last time though, we had the A over here and the R over here. It's already up, so it's slightly different this time. Okay, but since A is invertible, A can be written as a product of elementary matrices. That's where we start. Okay. All right, so now that we have this setup for A, let us multiply both sides by B. Okay, and remember, matrix multiplication is not commutative. So if you want A times B on the left, the times B on the right should also be to the right of this long product. Okay, you can't put it here on the left. All right, that does not work. So if you look at this long product on the right, all of the factors on the left are elementary matrices. So we can apply the same trick. If you want the determinant of A times B, you get the determinant of this long product. So there's one more factor of B, but you can again take out the determinant of the first factor, ET, and then the second factor, ET minus 1, and so on, all the way down to the determinant of E1, and lastly, the determinant of B. Okay, but wait a minute. Where have we seen this long product before? Ah, it is right there. So that portion of the right side is simply the determinant of A. And we still have the determinant of B, so we get the product formula. All right, so as we said when we started off with case 1, the other case would be that A is not invertible. So from our previous theorem, we now know the determinant of A has to be 0. But we still want to show that this formula still works. All right, so is the determinant of A times B still the determinant of A times the determinant of B? Okay, well, if the determinant of A is 0, then that product will be 0 times something, which we know has to be 0. Okay, so what can we now say about A times B? Well, we did have a theorem, and I did not put it in our list of review theorems because we're only going to use it this once. That theorem, 3.8.2, said that if the product A times B is invertible, then both A and B have to be invertible. Okay, so can A times B be invertible? No, because we know that A is not invertible. Okay, so since A is not invertible, then A times B is not invertible. Okay, and again, from the previous theorem says that the determinant of A times B has to be 0. And that completes our proof. In case 2, the determinant of A is 0, but the determinant of A times B will also be 0. So therefore, we get 0 equal 0. Alright, so let's do an example just for fun. So here's the matrix that we had in our previous example, and its determinant was 2, 2, 7, 4. Okay, so I made a copy of that matrix, and I've said before, matrices are very sensitive creatures. So they're almost the same. I changed 4 to minus 4, 0 to minus 1, kept the third row, 8, negative 2 instead of 12, 7 instead of 17. Okay, a few subtle changes here and there. Compute matrices determinant completely different. Well, there's still 4-digit numbers that begin with a 2, except now its determinant is negative. Okay, so what are we going to do? Well, let's multiply those two matrices together. So here is the first, and it's the second. And when you multiply them, oh boom, you get that matrix, and yeah, we expect to see bigger numbers. What is its determinant? Let me scoot that. Compute matrices determinant. Ooh, ginormous. 7-digit number. Is that the same as the product of these two determinants? So let's copy this and then multiply by this and click. Yep, of course, the theorem says the product of these two determinants had better be the determinant of this matrix product. Alright, so as a bonus of the last theorem, we can say something about the powers of a matrix. So remember that A squared is simply A times A cubed is A squared times A, and so on. And because matrix multiplication is associative, we can also write it as A times A squared. So, what does this theorem tell us? If you have any positive integer k, then the determinant of A raised to the kth power is the same as the determinant of k, which is a number, that we raise to the kth power. Now, what happens if A is invertible? Then we can also say that the determinant of A inverse is the reciprocal of the determinant of A. And we can write that as the determinant of A raised to the power negative 1. So it's almost like that minus 1 escaped the parentheses and became the exponent of the determinant of A. So maybe we should put square brackets there. That's not a matrix, that's just an ordinary pair of square brackets. Okay? So this tells us that if you have an invertible matrix, then the first property now generalizes. So maybe we shall also put brackets over there. So this time, if k is any integer power, then the determinant of a to the power k must be the same as the determinant of a quantity raised to the power k. Okay, so let's just illustrate this second property. This is not very obvious. So I copied our original example. Its determinant is 2274. And we saw its inverse. Compute matrices inverse. There it is. Okay, and again, that 2274 appears. What is the determinant of this matrix? It should be the reciprocal of 2274. Compute matrices determinant. Yes, 1 over 2274. Correct. Shall we do a square or a cube? Why not? We have time. It's a short video for a change. So here is our matrix. Let's take it to the third power. Okay, there it is. Okay, so yeah, huge numbers. So what is the determinant of this matrix? It should be the cube of 2374. Compute matrices. Determinant. Huge number. That might cause your calculator to overflow. Let's just check. Take that cubed. Do we get yep, exactly the same number? Okay, that is our video for today. So this is Jude Socrates signing off and telling you that S is for Socrates. As usual, you will find me on Facebook, and you will find the 4th edition on Facebook and at kendallhunt.com. So until our next video, I hope you enjoy the rest of the day. Bye-bye.